So this video is going to be looking at heat transfer and how to do some of the calculations associated with it. And we are going to do multiple labs or experiments that will kind of cover this. We've already done one, which was heat while cool, where we were transferring hot water and cold water and seeing that they came to the same temperature. So in your notes, write down heat transfer. And we are going to use Q as our symbol of heat. And we're going to have a negative Q and a positive Q. Negative in chemistry is going to signify that you are losing something. Positive means you are gaining something. So if we think of the hot water and the cold water transfer that we did with heat while cool, the hot water was losing the heat to the cold water, and then they were coming to the same temperature. So when we are doing these types of calculations, when we are transferring something hot to something cold, we are going to set them equal. And we're going to make something negative because, again, it is losing heat to something else. But you're going to see why the negative is going to be so important. So for heat transfer calculations, please understand that we're going to be using the specific heat of water, which is lowercase c, which is 1 calorie per gram degree Celsius, or 4.18 joules per gram degree Celsius, which is the more common one, but I will show you where you don't necessarily have to use the 4.18 all of the time. So we are going to do this problem together. So take a moment and copy it down. So we're going to have 75.2 grams of cold water at 22 degrees Celsius is added to 24.9 grams of hot water at 82 degrees Celsius. What is the final temperature of the water? Assume there is no loss of heat to the surroundings. So again, we are making some assumptions when we are doing these types of calculations, but for calculation purposes, we are always going to assume that all of the heat has transferred. So we're always going to set it equal. So just keep that in mind. In terms of lab error, again, you are going to lose heat to the container or to the opening or whatever you have. So we're going to work this problem together. Okay, so Q is equal to Q. Okay, hot equal to cold. So we are going to be using MC delta T for our calculation because we must always calculate heat. Temperature we can measure, but we are always calculating heat. All right, so this side of the calculation is going to be negative. Well, why that's important is when we are calculating delta T, we are always taking the final temperature minus the initial temperature. Well, in the case of the hot water is starting at 82 degrees Celsius, and we know it's going to go down. So its final temperature is always going to be lower than the initial temperature, so it's going to end up being a negative delta T. So if we take a negative of a negative, it's going to make it positive. So you'll see that when we do the calculation here. So for the hot water to cold water, and we're trying to find the final temperature, you must set them equal to each other. Okay, and there's multiple ways you could do this. So we're going to start with the hot water. We have 24.9 grams of hot water. The specific heat of water is 4.18 joules per gram degrees Celsius. And I have my final temperature, which I'm trying to find, which I'm going to set as X, and my initial temperature is 82.0 degrees Celsius. Okay, so I have 3 sig figs is really what I need to keep in mind. Okay, so I'm going to put it in brackets and put a negative on the outside because that X I know is going to be a lower number than 82. That's going to be equal to your cold water. Okay, so they're going to end up in the same container. So that is why I could set them equal, okay, because I'm going to transfer. So if I'm transferring, I could always set them equal. So 22 degrees Celsius is going to be my initial temperature of the cold water, 75.2, and I'm going to use the specific heat of 4.18. Now, if I set these equal, 4.18 is on both sides. I could also set this equal to 1 calorie per gram degrees Celsius as well. Okay, since they are the same on both sides, they are really irrelevant to our calculation. So I could actually just divide them out because they are the same on both sides. So I'm going to take my 24.9 grams and multiply it by x, or multiply it to x minus 82. And that whole thing is going to be a negative. And then I'm going to take 75.2 times my x minus 22. So I'm going to divide both sides by 24.9. And again, there's other ways you could do this calculation. I'm just trying to show you some of the algebra. So I'm going to divide by 24.9 to get rid of this 24.9. So I'm going to end up with negative x minus 82 over on this side. And this is going to end up being about 3.02 times x minus 22. Then I'm going to distribute my negative. So this is going to be negative x plus 82 is equal to 3.02. I'm going to multiply this out times x minus 3.02 times 22 is about 66.44. And we are going to have some rounding issues along the way. So then I'm going to gather all of my x's to this side. So I'm going to bring negative 3.02x over here, and I'm going to bring the 82 and bring it over here. So I'm going to subtract it from both sides. So I am going to be left with a negative 4.02x on the left. And when I add these up, and they are both negative, negative 148.44, I then divide it by negative 4.02 to get my x, and my x comes out to be 36.9 degrees Celsius. That's what my x turns out to be. So when you're doing this type of calculation, when you're setting them equal and you're trying to find the final temperature, just understand that the specific heat is, and we're talking water here. If we are transferring other things, then you can't necessarily cancel that out. But in this case, you can. Another way you can do the calculation is you could make the, no, you can't do it that way. But when you are doing these types of calculations, always consider that you're setting one thing equal to the other. So for a worksheet, we're going to give you a couple examples like that where it's hot and cold water that you are transferring to each other, okay? But sometimes you're going to see that we are putting in a piece of metal into the water, okay? So if we're taking something like an aluminum object and putting it and warming it and then putting it into water, you can't necessarily cancel things out because one side would be the aluminum and one side would be the water. So the aluminum would have its own specific heat and water would have its own specific heat. So please understand that this setup only works when you're adding hot to cold water. But the idea of hot to cold equaling each other is going to be an overarching theme that we're going to keep coming back to. So hot and cold equal, again, assuming no loss of heat, is going to be a type of calculation you're going to see going forward.